All right, welcome back to the drafting table for today's explainer, where we're going to unroll the exact engineering blueprints of how Solana moves massive blocks across the network. If you've ever wondered about the absolute mechanical precision required to achieve Solana's speed, well, you are in the right place. We're going to tour these schematics and really understand the architecture at a granular component level. So let's just dive right into it. Before we even look at the solution, we have to understand the fundamental bandwidth nightmare of trying to deliver massive amounts of data at scale. Think about it. Block producers are generating gigabytes of data. If they try to push all that data to thousands of nodes at the exact same millisecond, the physical infrastructure of the internet simply buckles. You just can't brute force your way through network physics. Enter Turbine. This is the elegant mechanism acting as the distribution engine for the entire network. Now, the definition sounds pretty simple, but it is incredibly powerful in practice. Turbine doesn't just send raw data. It literally slices it up and pushes it through a very specific, layered forwarding structure. It completely takes the burden off of a single node and distributes that workload across the entire network. This comparison absolutely nails why Turbine is so necessary. On the left, you've got naive broadcast. That is your classic bottleneck. It's like a single, incredibly stressed-out mail carrier trying to hand-deliver a massive package to every single house in a city simultaneously. Just a total logistical nightmare, right? But on the right, Turbine replaces that bottleneck with staged multicast. The leader only sends data to a few nodes, who then forward it to a few more. This allows the leader's outgoing load to scale sublinearly. And sublinear scaling, that is the magic word for true network scalability. Here's our blueprint for today. We're going to trace a single block of data chronologically, hitting the delivery problem, the leader and packetizer, the forwarding fanout tree, the repair subsystem, and finally, assembly. Let's kick things off with section 1, the block delivery problem. Basically, the bandwidth nightmare at scale. Look, forcing one single block producer to upload gigabytes of data directly to thousands of validators simultaneously is just physically impossible. You're going to hit hardware limits, bandwidth limits, ISP limits, the whole shebang. If a network requires a leader to shoulder that entire burden of distribution, it will absolutely never reach the transaction speeds Solana is known for. The peak bandwidth demand would just instantly overload the leader, causing dropped data and bringing consensus to a grinding halt. So, moving on to section 2, leader and packetizer. This is where the machinery actually begins. The system operates on a really strict separation of duties. It's all about delegating. The leader, its main job is to produce the block, sign the header to prove its authenticity, and then instantly hand the heavy lifting straight over to a highly organized shredder, known as the packetizer. The leader gets right back to producing, while the packetizer takes on the grunt work of splitting, sequencing, signing, and emitting all that data. And what exactly comes out of that shredder? We call them shreds. The packetizer slices that massive, unwieldy block into these tiny, manageable, fixed-sized payloads. But it's not just blindly chopping them up. It stamps every single shred with crucial metadata, sequence numbers so we know the order, offsets, and most importantly, a cryptographic signature. This is a huge deal because recipients further down the line don't have to wait for the entire block to verify the data. They can verify each individual shred independently in real time. Which brings us to section 3, the forwarding fanout tree. This is staged multicast in action. So instead of direct delivery, Turbine uses this beautifully layered cascading tree setup. The leader takes those fresh shreds and sends them only to a very small, select first-tier set of peers. Boom, the leader's job for those shreds is totally done. Then, those first-tier peers forward the data to a second-tier set, and it just spreads outward exponentially, like wildfire. And the best part? It's all pipelined. While the network is busy forwarding shred number 1, the leader's already pumping out shred number 2. Now, the actual shape and depth of this tree depend on a critical variable called the fanout factor. This is basically just the number of peers each node is responsible for forwarding to. It's a massive balancing act. A higher fanout factor means the tree is shallower, right? Fewer hops to reach the edge of the network, which is fantastic for latency. But it also means each individual node has to handle way more traffic, upping their bandwidth load. It's a pure engineering trade-off tuned for optimal performance. All right, section 4, the repair subsystem. Think of this as the network's paranoid safety net. Because transit across a global network is never perfect, packets drop, things happen, nodes are constantly, obsessively monitoring their incoming sequence ranges. They compute exactly which shreds they're missing. When they spot a gap, they do not wait around. They instantly fire off targeted repair requests to their neighbors or a dedicated repair service.
And they don't even necessarily need the exact missing piece back. Thanks to sophisticated erasure coding, they often receive redundant parity shreds, meaning even if a repair packet gets dropped, they can still mathematically reconstruct the missing data.
The underlying philosophy here is an absolute game changer. This repair logic is tolerant and asynchronous. It doesn't just panic over temporary gaps. A node isn't going to halt everything and scream, "Wait, stop the network, I'm missing shred 42. No way. It just keeps processing what it has, fetching the missing pieces asynchronously in the background, making sure forward momentum never stalls.
Finally, Section 5, Assembly and Final Thoughts, putting the finished product together.
Guided by the gossip layer, which is essentially the network's dynamic, real-time address book, nodes always know exactly who they're talking to. As these shreds arrive, the nodes are running incredibly lightweight signature checks on the fly. They buffer these verified shreds in write-ahead storage, and once every piece of the puzzle is finally accounted for, bam, the pristine, reassembled block is bundled up and formally handed over to the ledger storage and the validation pipeline.
This separation of concerns right here, this is the secret sauce of Solana's architecture. By isolating production, packetization, forwarding, and repair into entirely separate components, engineers have built a system where each part can be optimized completely independently. Find a better way to compress shreds? Update the packetizer without rewriting consensus rules. Find a faster routing algorithm? Update the fanout tree without breaking the repair subsystem. It is modular engineering at its absolute finest. So, what should you actually take away from all this? Well, understanding this blueprint is your ultimate diagnostic tool. The next time you're observing network data and seeing dropped blocks, you don't have to guess anymore. Is it your connection to the gossip layer? Is your fanout factor totally overwhelmed? Are you relying too much on the repair subsystem? This entire network relies on an incredibly high-speed ballet of data. So I'll leave you with this final thought. If you were tasked with redesigning just one layer of this blueprint to make it even faster, where exactly would you start? Thanks for joining me at the Drafting People today.